Okay, in today's exercise, we want to search a binary search tree for a given number and return the greatest value that is less than the number we're searching for. So if you look at this small binary search tree here, having 7 nodes, if we search for 17, we would return 14 because that is the greatest number that is less than 17. If we were to look for 10, we would return 9 because that is the greatest number that is less than 17. So now the basic nature of the problem here is that if we start with a number, let's just say 17, we're trying to keep traversing this tree until we sort of get to the end of the line because we want to look for the greatest possible value. In other words, say we go to the top and we look at 20 and we say, well, 17 is less than 20, but let me try to find a number that is less than 17, but it's the greatest number we possibly could have, right? So if we go to the left here and we say, okay, maybe your child to the left, which is lesser than you, maybe that's less than 17. Let's try that. Okay, 9 is less than 17. But do we want to stop there? Well, the answer is no, because maybe there's a value that's greater than 9, a child to the right, that is still less than 17, right? So basically you want to keep going until you can't traverse the tree any further, which means that there's just no more children in the direction that you want to go. So either you need to go lesser than, and there's no child there, or you need to go to the right, and there is no child there. So let's just kind of see what that looks like and then what we do in different circumstances. Now for 17, we would traverse here and say greater than 9, yes, greater than 12, yes, greater than 14, yes it is. Now if it's greater than 14 and there's no child to the right, then that must be the largest value. So that would be the value you want to use, right? So let's start with that use case. So first of all, I'm going to use Ruby here as my language, and I want to make a class to facilitate storing these nodes. So I'm going to say node equals struct.new, and I'm going to have a value. I'm going to have a left child, and I'm going to have a right child. And I'm going to construct my tree here. So it starts with the 20, 9, and 25. So node.new 20, I believe we said 9, and node.new, 25. So 20, 9, and 25. Now the 9 has a 5 and a 12 here. So the 9 has a 5 and a 12 here. And the 12 has an 11 and a 14. So 12 has, an 11 and a 14. Okay. And we've got everything there, I think, now. So we have 7 nodes. 1, 2, 3, 4, 5, 6, 7. Now let's make sure that, yeah, we clearly have a typo here. Let's make sure we don't have any more. And let's just pretty print the node itself. But we're going to call this maybe tree. It's our binary search tree. And let's just see what this looks like. Okay, we have an area. Oh, true. Why did I say that? Tree. That was funny. Okay. Got booleans in the brain here. So that generally looks reasonable. Everything's compiling. It's executing correctly. So let's go ahead and make a function here that's going to get us our answer. So we're going to call this, I guess, def greatest lesser. And it's going to take the number and it's going to take the node that we want to inspect. And what we're basically going to do here is say puts greatest lesser. And the value we're going to look for to start with, as we said, is 17. We're going to give the tree as our top node. Remember, the tree itself is a node. So we can just feed that in and we can recurse downward. And we know this should return 14 because we started with that example. So going from left to right, we can say there's 2 cases here we care about, right? One is if the number is less than the node.value, we do one thing. Else if the number is greater than the node.value, we do something else. We're not going to concern ourselves with the equality case because we just don't care about it for this example. We're going to keep things simple. How we would handle that is TBD. But keeping it simple with just the greater than or less than case, if the number is less than or equal to, let's just go ahead and say we recurse. So if the number you're looking for is less than node.value, like we're going to start with 20, let's just say, and we have 17, then we want to continue to recurse down the left path. So we're going to say num node.left child. Else if it's greater than that value, we're going to say greatest lesser num node dot right child. Okay, so let's see what happens if we run that. And eventually we get to undefined method value for nil class. And that makes sense because if you think of us trying to recurse down this, we're going to say 17, okay, you're less than 20, greater than 9, greater than 12, greater than 14, so let's try to recurse down your right child. Oops, you don't have one. So we need a guard clause here to protect ourselves from that. So we want to say if node.rightChild, only then do we want to recurse, else do something different. And what is that thing that we want to do here? Well, in that case, we know that if you are, the number we're looking for, if you are greater than the node that you're on, but there's no right child, then that node must be the value that is the greatest value that is less than yourself. So in that case, you could simply return the node.value. So if we run our test again, we get 14, and that is exactly what we expect. Now let's go back to our other example. We said if we have greatest lesser of, I believe we said 10, that should be 9. Let's go back and make sure that makes sense. So 10 is less than 20. It is greater than 9. And, oh, but it's less than 12. But it's greater than, oh, let me go to 11. And, it's also less than 11, right? So let's do that. Let's imagine that we pass that in, and let's see what we get. Okay, same problem, undefined method value for no class. And it's the same kind of problem we had before, except that now we're going to the left instead of the right. We're trying to traverse down the left child of 11, but there isn't one, right? So what we're going to do here is say, sure, you know, if the node has a left child, then let's continue to recurse that direction. But otherwise, what are we going to do? And this gets really interesting because now we have to ask, what do we do? Well, if you look at this 11, let's say we're trying to insert 10 here, right? We don't actually want to insert it, right? We're not actually inserting things into the tree, but it's kind of the same process to get to our final node. But then once we're there, we now basically want to say, well, let's go back up the tree and let's find the earliest value where the direction we went was a greater than direction. In other words, we went to the right. So at some point to get all the way down here, we had to have taken a turn to the right, meaning we were greater than that node. And that would have been this path right here, right? Because we were coming down with 10, and we were like, okay, let's go to 9. Oh, we're greater than 9. Let's go right here. Then we came back left. So we're basically trying to find the most recent time that we went to the right, and it's going to be that value. So we're sort of ascending now instead of going down. So what we want to do instead is call something like, I guess it'd be ascend till greater, maybe? Num. And then we're going to just pass in what node do we want to pass in, and what is that actually going to do? Well, let's imagine it's the current node. So how would this work? We're going to take the node that we're on, and we're going to simply ask, were you the right child of your parent, right? And that's basically a simple thing to ask because you're just simply saying, am I equal to, like for instance, 12 is the right child of 9. It was greater than 9 because it equals the right child node value of 9. Another way you could look at it is that 12 is greater than 9, right? So you can just do the comparison again. That might actually read a little better. We have two options here. So let's just say we're going to ascend till greater node. So now we're going to do def ascend till greater. And we're going to take the number and, actually we don't need the number, we just need the node. And so what are we going to do? So we're basically going to say if node.value is greater than node.parent.value, then we know that the most recent value that we saw, that value that we're greater than is the value we want. So we're just going to return the node.parent.value. Else, we're going to just keep ascending and say ascend till greater, and we're going to just say node.parent. It is that simple. There is one little problem with this, of course, right? So, oh, by the way, I'm passing the number here. I don't know why I thought I needed to do that. I don't. So let's run this, and the problem we have is that there's no method called parent on this thing, right? So we can make a method called parent by just attaching it as a property to our class. The problem with that, though, is that if we set this up, no parent values are set here, because when we made our tree, we never assigned those. Now we could pull out each of these node assignments, and then after, first you would make the child node, and then you make the parent, then make the child, and set the parent explicitly. That would be kind of verbose, and it would break our nice little tree structure here. So another way we can do this is to just intervene in our node class here and say def initialize, have our value, have our left child, and it may not be passed because in some of these cases there's no left child like this or right child. So we'll just say like right child equals nil as well. And we're just going to call super to get the basic functionality of the struct like we want. But we're also going to say that if there's a left child, we're going to use this ampersand. That's like a safe navigation operator. It says don't do this if it's not, if there's no value there. If it's nil, just don't like skip over this value, this assignment. And so I'm going to say dot parent equals self meaning this instance that we're on, and then also right child ampersand dot parent equals self. So now we're going to assign the parent, right? And so now, indeed, we get 9. We're just traversing up until we get to the node where the parent right child value is the node that we're on, and then we know we can stop. So to kind of look at this again, here's our code. So we are going down until we can go down no further, and then we're going to traverse back up. Now, one kind of thought experiment to walk through here maybe is that you can kind of generalize this problem here, because when you get to the case where there's no longer a right child and you say node.value, in theory, you could actually pass the same thing, ascend till greater on this node, because this node is greater than its parent node, and that would still work. The reason you don't have to do that is because you already just did this check right here, and you said, hey, am I greater than the node value? So you already know you're greater than the most recent thing, so you just don't have to do that. You can shortcut it and say, I'm already good. Here we go. But it's interesting. It's basically the same heuristic either way. So that is that, and thanks for watching.